Good morning to everybody. It is my pleasure to be here and to present the result of my work entitled A Detailed Analysis of One-to-One Internal Resonance in a Generic 2 Degrees of Freedom System. I will start with an introduction and some motivation, then I will tell you about the two-dimensional system that we are going to discuss and to use for illustrating the one-to-one internal resonance. Then we'll focus on free dynamics, some examples, and then some conclusions. Internal resonance happens when the ratio between two natural frequencies is close to an integer number, or more generally, when two natural frequencies become commensurable. 2 omega 1 is equal to 3 omega 2, and so on and so forth. Actually, there is a theoretical and practical interest since it entails nonlinear coupling in spite of the fact that the system can be linearly decoupled. Internal resonance can be welcome and exploited indeed, for example in gyroscopes, in tune mass dampers in bridges and buildings, and also for energy harvesting and many other applications. But internal resonance can be also unwanted and dangerous when not properly accounted for. For example, it is guessed that the internal resonance is at the base of the collapse of the Tacoma Narrow Bridge. Just hypothesis, but quite realistic. In any case, the internal resonance must be well known. And in this work, we will focus on one-to-one internal resonance, but the same ideas and methods can be applied to other internal resonances. Actually, one-to-one internal resonance has been deeply studied in the past, and the list of references is too long. So, what is new? What is new in this paper? What we are going to add? We note that in previous paper addressed a specific aspect of one-to-one internal resonance and specific mechanical systems. And the general, unified and comprehensive analysis of one-to-one internal resonance is really missing. And this is our first goal. Full understanding of the dynamical behavior around the internal resonance considering generic quadratic and cubic nonlinearities without any restriction on them. For example, the system is not requested to be conservative. I mean, we would just want to do a general, unified and comprehensive analysis. The second motivation is that, as we will see, the occurrence of some interesting, unexpected and previously unknown phenomena which add to the previously known one. So we have some knowledge basically. And the third objective is the possibility of tailoring the nonlinear stiffness to obtain desired outcomes. Please note that exploiting nonlinear dynamics is one of the new frontiers for the nonlinear dynamic system theory applied to engineering. Let's go to our mechanical system. After a preliminary model decomposition that decouples the linear part, the equation of motion for a generic, arbitrary, 2 degrees of freedom system subjected to an external excitation are the one reported here. And you see that we have any generic nonlinearities, geometric nonlinearities up to the third order, of course. We limit to the third order. But up to the third order we have all nonlinearities. The hypothesis is that damping is assumed to be decoupled and linear, excitation is assumed to be harmonic, that we have no nonlinearities in the inertial terms, and only quadratic and cubic geometric nonlinearities, as said. That means that we are considering moderate displacement and not large one. Moderate but not infinitesimal one, so not linear. And, which is very important for us, no restriction on the 14 nonlinear coefficients K, P and KQ. And this is the title and the main content of the talk. We will consider internal resonance, which means that the two natural frequencies are very close between each other, and then external resonance as well, which means that the frequency of the external excitation is close to both the two natural frequencies. We will consider an asymptotic solution obtained by the multiple time scale method. This requires some tricks, some mathematical tricks, introducing smallness parameters, rescaling the parameters, introducing some detuning coefficients which are named sigma internal and sigma external, and looking for the solution in the form of the asymptotic development with respect to these smallness parameters. Of course, the detail of the mathematical solution are omitted, but the solution I will report and I will discuss. The first order solution is this one. So we have basically a harmonic oscillation with amplitude AP and AQ respectively in the p variable and the q variable, and with frequency omega, which is the frequency of the external excitation. Then the second order solution, instead you have again oscillation but frequency 2 omega now, 2 omega, and the amplitude up are a square, ap and q, and aq square. Okay, after a long computation, you find that the ap, aq, phi and phi q, these are the phases of the solution, are solution of the two complex modulation equations that basically come from the solvability condition. These are two complex equations. Two complex equation means four real equations. With these four real equations, you can obtain in general your four unknowns. Functions of the excitation amplitude, excitation frequency, which is reported, which is inside is the tuning parameters, etc. And here are the coefficients that appear in the previous equation. We will not consider the general case because of lack of time. I will consider only the free dynamics case. Free dynamics means that no damping and no excitations. And in this case, the modulation equation simplified to two real equations, this one and this one, that are much simpler than the previous one. And C is a term that is equal to 1 if the P solution and the Q solution are in phase, and it is equal to -1 if the P solution and the Q solution are out of phase. You can rewrite the previous equation by going back to the physical variables, I mean to consider PA as a function, as AP epsilon, and so on and so forth, and again writing the detuning as a function of the external excitation, that now is no longer external excitation because there is no excitation, it is just the frequency of the oscillation. You have to remind that the solution is looked after in this form, so omega is the frequency of the oscillation. Okay, if you do this and put inside your previous equation, you get these two equations in the variable PA and QA. Two unknown, and you can solve this in principle. The goal is to determine PA as a function of omega. Omega is the frequency of oscillation, as said, and QA as a function of omega. These are also known as backbone curves, and this is exactly what we want to obtain and what we want to discuss. Okay, first of all, we can start by eliminating omega from the previous equation. You solve the first equation with respect to omega, the second equation with respect to omega. You compare this one, rearrange. After some algebra, you get this equation where unknowns are PA and QA. It is a fourth order equation that permits to compute PA as a function of QA, which means the solution in the displacement space. How one variable depends on the other. In other words, the solution of this equation provides you the nonlinear coupling between different modes. Since it is a fourth order equation, we can have no solution, two solutions, or four real solutions, and we will discuss these cases. First, we note that when omega p is close but not exactly equal to omega q, we have the following parametric representation of the solution that helps very much in drawing the pictures, in understanding what happens. So it is an analytical solution basically, so not so complicated as it can appear. You can easily manage by a symbolic software. This is a function, the parameter for this parametric function basically is this eta. Eta is, apart from C, that it can be +1 or -1 as said before, is just the ratio between the variable q and the variable p. So you get this solution as a function of this parameter eta. Now let us focus for a while in the perfect resonance when omega p is exactly equal to omega q, and in this case the previous equation, basically this equation simplified to that one, and only the parameters eta appear as an unknown, so that you can solve it in principle computing eta. And this means that P as a function of Q is just given by this expression, and it is a linear function of Q. P is a linear function of Q. And please let's agree with me that the fact that nonlinear coupled oscillation have a linear coupled solution in perfect resonance is a little bit unexpected, at least for me. And the backbone curves for this case are reported here. Please note again that here we can have no 2 or 4 real solutions. Okay, and the sign between the square brackets, the sign of this term basically, the sign of this term tell you if the solution is hardening, if the sign is positive, or softening if the sign is negative. And the sign can change on different solutions. So we can have that simultaneously softening and hardening behavior on different backbone curves ensuing from the same natural frequencies. This is quite strange, not really totally unexpected. There are some examples before, but it is quite strange. Again, not totally unexpected. Okay, the previous modulation equation that we reported here, I said, can have no 2 or 4 solutions. Let us discuss these 3 cases. 2 solutions are expected, in fact, no problem. This means that for each natural frequency there is a backbone curve. You have a 2 degrees of freedom system, you have 2 natural frequencies. From each natural frequency you can get 1 backbone curve. So this is the expected case, okay? But you can also have no solutions. What does means no solution? No solution means that the system do not have periodic solution around the rest position, not even for small amplitudes. No solution is solved. But since in the linear case the oscillation of course exists, this means that the introduction of the nonlinearity suddenly destroys the oscillation. And this is really an unexpected phenomenon that requires a detailed analysis for understanding if it is due to the multiple scale approximation or it is a real situation. What I mean, it's just the mathematical tool we use that fail in this case, or this behavior really happen in the system, in the real system. If it persists when higher order nonlinear terms are considered, for example, 5th order terms, so if it is robust or not, and what happens if really it exists, what happens to the solution, what kind of outcome you can get in that case, quasi-periodic, chaotic, etc. Okay, really fully understanding on this fact is left for future work. So now we believe that it is just a guess that no solution happen in this case. However, we have tried with numerical solution. We have a lot of trials, a lot of tentatives, and we have never found a periodic solution in that case. So it seems that, at least from numerical point of view, the result is confirmed. This means that no periodic solution are around this case. But again, this is a numerical partial confirmation that need to be confirmed in a very general and robust way. So up to now, it is just a guess. The last case is 4 solution, which means that there are 4 backbone curves ensuing from the now unique natural frequencies. Again, this is not so common, and somehow unexpected, but it's not so surprising as the previous result indeed. Okay, when you change a little bit the frequency between each other, so when you detune them, of course only of small quantities, because we are considering one-to-one internal resonance, you can have that the asymptotic expansion of the solution around these frequencies, QA function of PA cube, and PA is a function of QA cube. So you have a cubic, and then for quintic, and so on, coupling. So no longer linear, as said here, and this means that the perfect internal resonance, where PA is a linear function of QA, is a singular or structurally unstable case. Because if you detune a little bit the perfect frequency, you pass from linear coupling to cubic, quintic, nonlinear coupling. So this is really a structurally unstable situation. And also this fact has not been sufficiently highlighted in the past literature. Okay, let's go to some examples. And these examples are aimed to show the many possible scenarios that can be gained by varied nonlinear stiffnesses, quadratic and cubic. And the considered cases are chosen to illustrate the main different behaviors that may occur, but not all of them, only the main. And the considered stiffness do not necessarily represent any specific real system, but can be expected to use in other new real systems, tailored exactly to get that behavior. And the theoretical results are always confirmed by numerical simulation of the original to the degrees of freedom system, so that we believe that this result, even if they are obtained by an approximate solution, are really happen. Okay, the first case is given by these values, the parameters. You see omega p is 1 and omega q is 1.1, so small detuning, very small detuning. And this is the case we name A, where the previous solution you mentioned have the previous equation has two solutions. And in this case, we get that one backbone core is softening, the P branch, and on the other end, the backbone core of the Q variable is hardening. So we name it softening, hardening behavior. And we have only two backbones and two asymptotes, and we will see. This is the solution in the displacement parameters. This is an enlargement, and this is a much larger view that show you how this goes to two different asymptotes. And you see here, since you are not in perfect resonance, you have that linearly the modes are decoupling, and the coupling occur only on the nonlinear regime. No linear coupling, because we are not exactly in perfect resonance. Okay, here the same picture before in 3 dimensions, which tell you much better how the backbone cores bend toward both variables. Okay, the second case is what we name B, and it is the case where we have no asymptotes, so no solution of the previous equations. And for example, in this case, we have that the backbone core ensuing from the omega p, which is 1. This one is hardening, you see, and also the one ensuing from Q is hardening. And now, instead of have two unbounded backbone cores, you have a closed loop for the backbone cores. And you see, the analytical prediction is confirmed by numerical simulation. So this behavior is real. This behavior is true. It's not just a mathematical phantom. Okay, this is the closed loop in QP parameters, which confirm the previous result. Okay, let's go to the third example. The third example, which we name C, is the example where we have 4 asymptotes. So in this case, we have that the P branch is hardening, you see this one. Also, the Q branch is hardening, it is reported here. So we name it hardening case. But on top of that, we see that we have a new path. Not a branching one, not a backbone core, just a new path that, to the best of my knowledge, has not been discovered before. So I believe that it is a new phenomenon that has been highlighted around one-to-one internal resonance. You can have a different new path. You can see the new path also in the QMPA phase parameter plane, and again 4 asymptotes. Each of these branch go to one of the 4 asymptotes, including the new path. This is exactly what I just told you before, that a new path detached from the previous one and existing only for moderate and large amplitude occur, not reported before in the literature. And it has been confirmed by numerical simulations. So again, it is really happened. So it is confirmed by numerical simulations. Okay, other two cases where again you have 4 asymptotes. Here now you have that the P branch is softening and the Q branch is hardening. So we name it SH case. And again you see that the new path, the third branch occurs. And the C2 case, again 4 asymptotes. Here we have that both P and Q branches are softening. So we name it softening case. And again, we have the new branch occurring around the one-to-one internal resonance. Now, if you take randomly your stiffnesses, which one, A, B, or C, is the most probable case? Okay, what we get is this one. The two-solution case, which is the more expected indeed, in fact, it has the most probable. 73% of possibility randomly choosing the stiffnesses provide this kind of solution. And Within this, the softening case is the most probable, while the hardening case is very, very improbable. But the probability is not zero. Small but larger than zero. The case with no solution, which means that the case with a closed loop between the two natural frequencies, has about 10% of probability. What does it mean? It means that it's not probable, but it's not even rare. It's not rare. There are 1/10 possibility that choosing randomly your stiffness, you get exactly this case. And within this, you can have, you have that softening case is the most probable, and hardening case is very, very improbable, almost rare. Also, the 4 cases, not so common, but not rare, 70% of possibility, so quite large. And this is what happens if you choose randomly your sieves, cubic and nonlinear and quadratic sieves. That's it. Let's go to the conclusion shortly. We have studied the perfect internal resonance, and we have shown that it is a structurally unstable situation. We guess that there are some cases in which the perfect internal resonance, there are no periodic solution. We have found a cornucopia of different cases. Both modes can be hardening, softening, one mode hardening, one mode softening, modes in phase and out of phase, etc. And we have found the existence of an extra path that can appear close to the main backbone curves. As further develops, many are possible. I mentioned only the most important 3 from my point of view. To deeply study the case in which there should be no solution in the perfect internal case, I mean to prove it mathematically, rigorously that it is true, to compare the proposed finding with experimental result. We compare only with numerical result, but also we need to compare with experimental result, and to exploit the result for engineering design. Thank you very much for your attention.